Dr. McKim. One of the white sets is the syllabus. One of the white sets is the syllabus. Other white set is the first main handout. We'll start with chemistry of alcohols and ethers. The green is sort of a flow chart, reference sheet. I'll usually put sort of reference sheets on colored paper, although the outline is in the white set for this handout. Syllabus. Everybody got a syllabus? White set. In the future, let's don't sit on the back row, please. I think we have enough space. Okay. First off, we have to, class starts at 8 o'clock. Please arrive on time. Please account for traffic difficulties. I will arrive early also. We can't have people coming in late and disrupting class. We'll start at 8 o'clock sharp. Okay. I expect that you can read. Information is here. I don't need to read it to you. In terms of reading directions, following directions, there's a section on that. I expect that you read the section on reading instructions. Grading. The final exam in this course is the ACS comprehensive exam covering both organic 1 and 2. It's a 70-question multiple choice exam. Okay. National students across the country take this exam. There's some comments on grading. There's comments on studying. Please read. You'll see things like, I highly recommend you get a composition notebook, $1, and use it kind of as a journal. Write down your questions. You've got to learn how to ask questions. Get them answered in class. 10 minutes before class, I'm here. Good time to ask questions. Office hours, in the hall, if you see me. But you've got to have them written down because you may have 10 questions and then when you time to ask them, you can only think of 2 of them. Okay? If you had the other 8 written down, boom, we can get them. Boom, boom, boom. All right? Get you a composition notebook. It also talks about note cards. A lot of reactions in Organic 2. Making yourself note cards. Put the reaction on one side or whatever on one side, put the answer on the other. Not only writing it out is good practice, but then you have a study aid. Okay? The main thing about Organic 2, there's lots of material, it's organization. It's staying on top of it. Okay? And organizing the material is not difficult. It just takes effort. Okay? Would anybody like some note cards?
I do.
I saw his hand go up first, and I wasn't looking over there. We'll get you some though, because it might have been cut. What else I got for you? How about a ruler? Everybody needs one for lab. We start checking the lab today. If you have Wednesday, somebody already wants one. 6-inch ruler is fine. It might be used. Yep.
You got extra.
Unless I need the extras, just break it down in class. Okay. Thanks, guys, on that. Also need a Sharpie marker for lab. You know, everybody's got to have one. Have one today. That one is used. If it runs out. Okay, I expect you to read the syllabus. Back to the second page is our daily outline. Very tentative. After today, we'll already be behind. So there you go. It's not exhaustive. It's kind of the main topics. My background is in drug discovery, medicinal chemistry. My graduate degree is in medicinal chemistry. Discovery, development of drugs. I will use drugs to illustrate principles. I know a number of you are interested in medical fields, whether it be pre-med or PA, dental, a variety of others. Here's some common drugs. Many of these you have taken: Advil, Tylenol. These compounds, quite simple organic compounds, but they work miracles in the body. All these, we see functional groups: carboxylic acid, ether, carboxamide or amide, amine, phenols. You also see aromatic rings, benzene rings. Benzene is the kind of the granddaddy of aromatic rings. We'll cover the chemistry of benzene during test 2. It's 4 tests in organic 2 for me. Your lowest test is dropped. Although your drop test can replace a low quiz grade. Okay? More important for me, or just as important as learning the material, is what are you going to do to be successful after you graduate college? Okay? We really need to be tuned into that. I am. For you guys, I want you to be successful. What are you here for? Hopefully not just to take this class and get a diploma hanging on the wall. Anybody want to get a job when you graduate? I see a lot of hands go up. Here's a job ad. It's about 15 years old now, but they're made like this every week in like CNE News, ACS Magazine. This job ad reads like the syllabus for this course. A BS or MS in organic chemistry and experience in multi-step organic synthetic reactions. We'll be doing that. Purification of organic compounds. You'll hopefully be doing that in the lab. Temporary methods. Must have an understanding of fundamental reaction mechanisms. We'll be doing that. Functional group reactivity. That's what organic 2 is all about. Familiarity with spectroscopy techniques. IR, mass spec, NMR. Bristol Myers Squibb, great job, great benefits. They have weight rooms on campus. They have daycare on campus. Gourmet buffets for lunch. Drug companies take care of their people. Be a great place to work. Organic chemistry is very applicable, not only there, but to pre-med. Go take biochemistry, pharmacology, and medical school. But it's also more about grades. Here is a recommendation form. Students ask for recommendations. It's not just about your grades. That's actually a minor component. More importantly are things like well-knowledge of field, ability to apply knowledge, desire to learn, work performance, potential for growth, creativity, drive to accomplish, maturity. These are things that are important. And when you come to school, when you walk onto campus, believe it or not, faculty look for these things. Okay? Santa Claus is always watching. Just keep that in mind. Okay? You guys are all capable of getting top scores and everything here if you work at it and realize you need to think about it, as opposed to just going by your routine and being a student. Okay? My little sarcastic how to fail organic 2. Anybody want to do that? Good. If you want to, here's how to do it. Hopefully none of you do. It's unfortunate, though, that that's never the case. Okay? But this is usually why it happens. Stuff like this. Where are we at? The last sheet? The last sheet is to be torn off and turned in on Friday. You got to be able to do mechanisms. You got to be able to use arrows correctly, correct arrows to correctly show electron movement. Hopefully you'll learn this in Organic 1. Here's a mechanism question. It's very fundamental, has a number of products. You need to be able to show Lewis structures for products to see what bonds need to be formed. Please do this. I want to see how you move arrows. Okay, and you can do a basic mechanism. Turn this on Friday. We've got to take care of that before moving on. If you do not base your thinking on mechanisms, and instead if you rely on memorization, it's going to become an overload and you're not going to do well. By the way, you memorize, you have no idea what's going to be on the ACS exam. Some committee in Michigan makes it out. You need to be able to think broadly. Just like in math, you don't memorize the answer to every problem, do you? You have mechanisms or equations or ways to arrive at answers. I also like to get to know you a little bit, some miscellaneous questions, also just some survey questions. These are optional. Please turn this page in on Friday morning in class. Questions about the syllabus. Really, I want to take questions on Friday because I want you to look at it, write your questions down, but anything right now. Okay. What are we doing today? By the way, you asked me what we're doing. I usually will pull out the syllabus and I'll look up the answer. Okay. Or you ask me a question about grading, I'll pull out the syllabus because it's right there. I don't need to remember it. But you read about asking questions. It's okay to ask for clarification. Say, hey, I read this, but I just don't understand what do you mean here. It's certainly okay. Today we're doing nomenclature. Again, we're starting with alcohols and ethers, functional groups. We saw a little bit in Organic 1, but now we're going to kind of focus more on those functional groups. Nomenclature, SM1, SM2, elimination. The green sheet shows an overview. Really, front and back here, I think, is almost everything for test 1, an overview of everything, except for spectroscopy, NMR. Okay? And the first thing that we will do is we're doing chemistry of alcohols, and if you ever can't see, say, hey, I can't see. And I'll adjust. Alcohols, we can do substitution, elimination, alkylation, like Williamson ether synthesis. We saw most of this in Organic 1. We'll also do oxidation. That'll be brand new for us. Okay. First thing we're going to do is substitution. Then we'll move to ethers. And that's shown down there. And then on the back side. So that's an overview. Again, organization. This is a way to me to kind of give you an overview of what we're doing. Keep it organized. Keep me organized. But you need to organize the material yourself. Okay, guys. Chemistry of alcohols and ethers. Here. I've started doing kind of what I call a warm-up. It's kind of a version of what Dr. Hager does, but very differently. I use the warm-up to sort of just illustrate some chemistry, but with a real-world example. Also show you a type of problem that we might want to be able to work after we cover the material. Okay, just kind of a little teaser. Here's an example. Here's lincomycin. You may have heard of clindamycin. Anybody in the nursing field or clindamycin? If you go into the hospital, have a procedure, very often they give you an IV of clindamycin maybe, or there's some others. Antibiotic. There's clindamycin. Clindamycin is made from lincomycin. Lincomycin is a natural product. It came from some microbes in the dirt, in the soil. The microbes produced this. And some chemist or natural products person isolated it, characterized it, determined the structure, tested this in a biology assay, found it had activity. But then somebody started doing chemistry with it, and they found if you convert the OH, or if you substitute it with a chlorine, this molecule is even more potent. It had better activity as an antibiotic. So this is drug development. The question here is, how would you convert this to this? How would you replace this OH with a Cl? You probably answered that from Organic 1. We'll learn other ways here in Organic 2. So there's a question here. By the way, where was lincomycin discovered? Somewhere in Nebraska. Where was it? Lincoln, Nebraska, yeah. Okay, there's another warm-up here. Morphine. Yeah. It's a mechanism question. You take morphine, you eat it with ACL, you get a miraculous transformation, and you get what's known as apomorphine. Somebody discovered this back in the 1800s. They just cooked it up with HCl and they had a new molecule. They probably didn't know what they had other than they purified it. Okay. Mechanism. Now, this is a challenging mechanism, but it's basic steps. Anybody heard of apomorphine? Used for Parkinson's disease? So this new drug from morphine is now used as a drug itself. Okay, a couple of teasers. There's something below. All right. Y'all ready to get started? First thing we'll do is nomenclature of alcohols and ethers. Very similar to standard nomenclature from Organic 1. First off, we have terminology. There's always some terminology we need to know. Aliphatic or saturated alcohols. These are going to be alcohols where the OH is bonded to an sp3 hybridized carbon. Okay? On the other hand, you can have aromatic alcohols, but these are not really called alcohols, although you could. They're called phenols. Okay? We'll see those. If the OH is bonded to an alkene, that's called an enol. We actually saw enols in Organic 1 when we did tautomerization. Okay? Those are usually not stable, but they tautomerize to what? Carbonyl compound. Okay? Some enols are. We'll see more enols when we get over to test 4 and we get to carbonyl chemistry. Here's these are 3 saturated or aliphatic alcohols. Aliphatic is just an old term for just saturated. Ethanol is primary alcohol because the OH is on a primary carbon. That's primary because it's bonded to one other carbon. Here the OH is on what type of carbon? Secondary. Why is that secondary? Because it's bonded to 2 carbons. Here the OH is on a tertiary carbon because that carbon is bonded to 3 carbons. Ethanol, we all know ethanol. Isopropanol, sold at Walmart, 70%, 30% water, rubbing alcohol. T-butanol, you're not going to see in the drugstore, but it's a good solvent. Tertiary alcohol. And then phenol. That's just phenol itself. We can start putting substituents on phenol and have a substituted phenol. Nomenclature. As with alkanes, identify the longest continuous chain. Replace the E of the alkane with OL to indicate the presence of the OH functional group. Longest continuous chain in this one here. 1, 2, 3, 4. Yeah? What is that? Butane? So we got a longest continuous chain of butane. What do? Replace the E with what? OL? So what do we get? Butanol. Okay. Well, what is this? That's also butane with an OH, so we can call it butanol. What's the difference? We have to indicate where the OH is located. Here it's at, what do you want to call this in terms of numbering? 1. We're going to call that 1 because either end could be 1. Why do we want that to be 1? Because substituents get lowest numbers. This is called 1-butanol. Now a more descriptive name could be maybe 1-hydroxybutane. Does everybody see how that would also work? Butane with a hydroxy in one position. But that's never used that way. Standard IUPAC is to have the OL there to indicate that it has the OH and then the position with the 1. What do you want to call this guy down here? 2-butanol. Right? Pretty straightforward. What's the relationship between those two? Constitutional isomers. Same formula, different connectivity. The OH is connected to different spots. Okay? Okay, name the next compound while I'm erasing. anytime we're doing something like this, yes, it's okay to talk with your neighbor, nudge them, wake them up. Hey, what'd you get? Okay, longest continuous chain. What we got? 5? 1, 2, 3? No. 1, 2, 3, 4, 5. Either way you go, either carbon, you get 5 coming through here. Yeah? What is 5? Pentane. So we got pentanol. Right? Pentanol. What's on the pentanol? Where's the 1 end? This end or here? 1, 2, 3, 4, 5. What's on the, what do we got? The OH is in the OL. We don't have to call it hydroxypentanol. That would be redundant. We do have a methyl. What position? 2-methyl. 2-methyl pentanol, does that look right?
No.
2-methyl 2.
Ah, yes, we are forgetting. We got to locate the position of the OH. 2-methyl 2-pentanol, all one word through there. This tells us where the methyl is. This tells us where the OH is. Because we could also have a 2-methyl 3-pentanol if the OH was maybe there. How about the compound below? How do we name, if there was anything there, what would that be called?
Cyclohexane.
Cyclohexane. So that's where we want to start. What do we do with this E on the end? Change it to an OL. Because what type of compound is this? It's an alcohol. You could call it an alkyl chloride. But usually, if you have another functional group, chloro never takes precedence. Chloro is always going to be a substituent. Halogen would be substituent. So right there is cyclohexanol. And by the way, you don't need a number for that. What's on the cyclohexanol? Chloro. What position? 3. Good. By default, that's 1. You go this way. You wouldn't go this way because you'd get 5. This is 3-chloro cyclohexanol. Okay? Final exam. How many stereoisomers possible for that compound? Four. Who got it right? No? You got 2 chiral carbons. 2 to the 2 is 4, last time I checked. Right? Okay? Final exams, comprehensive. Things like that. You'd have cis and trans, and then each of those would have an antivirus. Ether nomenclature. Well, ethers have an oxygen, but it has R groups on both sides, right? Now, in ethers, the R can be really anything. It can be saturated, sp3. It can be sp2, and it's still an ether, and it's still quite stable. We can have terminology. Symmetrical ethers where the R groups are the same on both sides. Diethyl ether. Usually just called ether. It's so common. Ether was used in the Civil War to knock folks out for surgery. Okay? Breathe too much, you'll knock out. Breathe even less, you just get a bad headache. Don't do that. You can have non-symmetrical ethers. The methyl on one side, Me is methyl, yeah? CH3. I always do Me, usually. On the other side, what is that? Tert-butyl? Okay, you got to know your standard group name. This is called methyl tert-butyl ether. Now, that used to be used as a gasoline additive to get oxygen in gasoline. They phased it out because the MTBE was getting into the groundwater and it kind of smells. Now they put ethanol in gasoline, up to 10% on your gas tank. May contain up to 10%. When we see how to name ethers, you basically just name each alkyl group. Ethyl ether, but instead of saying two ethyls, you just call it diethyl. Here we have a methyl and a tert-butyl. Methyl tert-butyl ether. Unfortunately, whoever did this, probably some newscaster, I don't know. Butyl comes before methyl, so it's really not right in terms of alphabetical order. But it's too late now because it's known as MTBE. Then you can have, with ethers, they can be cyclic. The oxygen can be in the ring. Can't do that. When we say a cyclic alcohol, the OH has to be a substituent. But a cyclic ether, we're talking about the oxygen being part of the ring. This is a 5-membered ring known as THF, tetrahydrofuran. It's a cyclic ether. It's actually a common solvent, although I don't think we use it. I don't use it in organic 1 or 2 here. It's very common in advanced organic chemistry. Nomenclature of ethers, I've already alluded to this. You basically just state the two groups that are bonded, and then you say ether. All right? And it's actually 3 different words. The one position of each ether group begins closest to the oxygen. We'll illustrate that. Groups in alphabetical order, despite the NTBE. Name this one below. Let's do it. What do I see here? I see an ether. Because again, a halogen is not going to take precedence over hardly any other functional group. We're going to name this as an ether. So I want to have the 2 groups and then ether. Well, what's the group over here? Let's don't do common names yet. Let's do standardized IUPAC. Well, first off, we said the 1 position is the closest to the oxygen. So go ahead and call that 1. 2, either way you go, you get 3. Longest continuous chain is 3. So what do we have over here? Propyl? But there's something on that propyl. What's on it? Methyl. In what position? 2-methyl propyl. That's what that is over there. That's a 2-methyl propyl. What's on the other side? 1, 2, 3, 4. Please don't call that 5. I see it done. 1, 2, 3, 4. What do we got? Butyl. We're using the YL ending. That's 1, 2, 3, 4. What's on the butyl? 4-chlorobutyl. Unfortunately, well, I can just do this. How do we name it? It's 1 word, 2 word, then ether. These in alphabetical order, what comes first? It's this, and then it's a separate word here, and then what? Ether. The name of this molecule is 4-chlorobutyl, 2-methylpropyl, ether. Now, somebody did, I think, see, this does have a common name over here. What is the common name of this substituent? Iso what? Not isopropyl. When you do common names, it's all the carbons. Okay? That's propyl because it's straight chain and then a substituent. A common name, you say, hey, that's a 4-carbon group. 1, 2, 3, 4. But it's not a butyl. It's not a sec butyl. A sec butyl would have the methyl here. Isobutyl. Okay? You could have called that isobutyl. 4-chlorobutyl, isobutyl ether. Okay? Isobutyl group. Typically, I always ask for IUPAC. is good to know your standard common names, the one I introduced in Organic 1. Isopropyl, isobutyl, sec-butyl, tert-butyl. You can usually recognize a tert-butyl, it's like a cross. Yeah? Okay. Name the compound to the right. Ooh, it's a symmetrical ether. We can just use di, because it's the same thing. What is the group on the oxygen? Morgan, what you got? Pentane? It's not a straight pentane chain, it's a cyclopentane. But we're not going to say cyclopentane. We're going to have what ending? Dicyclopentyl ether. And that's a Y there. Okay? Dicyclopentyl ether. You don't want to call it cyclopentyl ether, do you? How about this guy down here? Benzene ring. What do you call a benzene ring when it's a substituent? Phenyl. Not a phenol. Phenyl with a YL. And that's a methyl. Alphabetical order, this would be methyl, phenyl, ether. But guess what? Nobody calls it that. As we'll learn when we do aromatics, this is known as, anybody know it? Probably not. Anisole. It's a common name. Lots of aromatics have common names. If you go to Lowe's in the paint section, you can buy toluene. What is toluene? It's methylbenzene. Nobody calls it methylbenzene. It's known as toluene. Okay? We don't need to know that now. Let me test 2 when we learn aromatic nomenclature.
Do you have to do dashes in between?
No, with ethers, it's 3 separate words.
Okay.
Or if you're doing dye, it's 2 words. There's no dashes here. Okay. Reactions. And I see, I didn't change this up here. We are now using the Klein book. Changes that has been made on the outline. Back of the 2nd page in the syllabus. Smith was the old book. I don't go directly by the textbook. Okay, any organic book has similar material. As it says in the syllabus, please make use of the index. But I do give you the chapters on the outline. What chapter are we in? Not the outline, the daily outline, the daily. Chapter 13, yeah, that's the Klein book. Not chapter 9. All right. Okay, back to the green sheet. What's the first reaction type we're going to do? Substitution. Okay, so here we go. Substitution reaction. The OH is a poor leaving group for rate determining steps. You must have an H plus present to create a better leaving group. Typically, you need to make the oxygen positive to make it a better leaving group for a rate determining step, like in an SN2 or SN1. Why do I refer to rate determining step? Because in this class, we'll learn substitution mechanisms in which the leaving group does not leave in the rate determining step, but rather leaves in the fast step. And if it leaves in the fast step, guess what? You don't have to protonate the oxygen. It's just an easy step. For the mechanisms you know, the OH has to be protonated. Or you can convert it to a tosylate, but that's a totally different thing. First reaction is a reaction of an alcohol with HX, which typically means HCl, HBr, etc., to give what? Alkyl halides. We can essentially convert the OH to a halide. Convert's not the right word. We're not doing nuclear chemistry here. Replace or substitute. By the way, that's what was needed to go from lincomycin to clindamycin, right? Replace the OH with a chlorine. Okay. We did this in Organic 1 with like HBr. In fact, we did a lab, right, where we did shaken, not stirred. Wasn't that an OH to Cl? We'll also learn other reagent stuff. So this is a lot of review. First reaction I'm showing here. I got a primary alcohol with HBr. React that to get this alkyl bromide. Obviously a substitution reaction. What's the mechanism? You only know two right now, is that right? You only know two mechanisms for substitution, SN1 or SN2. Which one is it here? Because it's one of those. SN2. You should never make a primary carbocation, would you? Usually not. This is just a good old SN2 reaction. What do you want to do first? Protonate the OH. HBr. It's okay to just go ahead and show it ionic for me. All right? Or you can show it covalent. I'm okay with just starting here. Okay, these electrons. I told my guys in Organic 1, when you start with moving the arrows, the first thing you want to say in your head is these electrons. Every time you move an arrow, say these electrons. And I want to say these electrons, and usually I'll circle them, especially if it's a long pair. These electrons go and make a bond to the proton, the acid, the H+. What does that give? We now have an oxygen with two bonds to H. I'm going to draw that bond out. How many lone pairs left? Only one. Positive charge. We just protonated the alcohol. To protonate an alcohol, you need a strong acid. You're not going to protonate an alcohol with water. You're not going to usually protonate an alcohol with a weak acid. Strong acid. That's why HX works. You could also use maybe sulfuric, phosphoric. HF works. Okay, from here, what do we want to do? We're working towards the final product. We got Br minus around. What you want to do next, Antonio? Hold on, if that, you mean leave first or what? You want this to come in, these electrons to come in and kick that off? Right. What does that give? It gives final product plus what? Plus water. There you go. You just protonate and then you do, what mechanism did we do right here after the protonation kind of activation step? What did we just do here? We just did the good old SN2. Backside attack, kick off the leaving group, all concerted. And you know everything that goes with SN2, hopefully. If this was chiral, we would be doing an inversion. We know kinetics. You need to look back and review all the details of SN2. Okay. So what did we just do there? We converted the alcohol to the alkyl bromide by an SN2 here, but we didn't have an activation step. How about the next one? I see a tertiary alcohol with HCl, and I've got this alkyl chloride. I've got some stereochemistry to begin with. What do you want to do first in this mechanism? Protonate. Usually under acidic conditions, the first thing you always do is protonate something. Got HCl. I'm going to go ahead and just, is it okay? Can I just protonate this? All right. Can everybody show protonation of that on a quiz or test? Or do you want me to show it every single time? If I show it every single time, that's going to take about an hour over the course of the semester. And I think you'd rather spend that hour on something else. Okay? So I'm skipping the pre-activation step, but you can't skip that on a quiz or test. Refer to above. Okay, we got a protonated OH. What do you want to do next? We somehow got to get the leaving group off and got to get the nucleophile on. How do you want to do it? What mechanistic? You want to do what? I'm going to take a guess and say Adam. Sean? Sean? Yeah. There's another Sean. 3 Seans? There's only 2 on my roll. We need to check it out. You're on my roll. I don't know that you are. We need to make sure. Tell me again.
What?
Sean.
The leaving group's going to leave first because it's an SN1 reaction.
Good. Ionization, what do we get? Right there. That's gone. I got a phenyl and that's a methyl, right? What type of stereochemistry is this carbon going to have now? Do you want me to draw an ME there? An ME here? I like putting MEs on the end because it just makes it more clear. That's a methyl on the end. What is this carbon now? What do we need to show? Carbocation, right? Plus what? Water? Leaving group left, it ionized off. Is this possible? What type of cation did we make? Tertiary. Not only is it tertiary, but this is the benzene ring. It's resonance stabilized. Right? I need to draw this benzene ring out, the phenyl. We can do resonance. In fact, let me take the time to do resonance. Windshield wiper, over. Resonance double-headed arrow. And we get boom, boom, boom. Okay? But there's more resonance. We can draw 2 more. These can come up here. You should draw the others. I can take a quick look at it. Resonance stabilized tertiary carbocation, so ionization, yes. We certainly would, the Cl minus is floating around. We certainly don't want it to do a backside attack here and kick that off because we never do backside attack, we never do SN2 or tertiary carbon. Tertiary. What's the stereochemistry now of this carbon? Or what's the hybridization? It's sp2. What's the geometry of sp2? Planar. Planar has no stereochemistry. Okay? It's planar. It's flat on the board. There's nothing forward or back. It's just flat on the board. Now what's the next step? We've got to make the bond here. These electrons do what? Boom. They just add. Why don't they add here? I mean, that's the cation. That's part of resonance. Typically, you never destroy your benzene ring. If we added here, we'd have a chlorine there and all this. The benzene ring would not be intact. So the transition state to this product is lower, but just keep that in mind. Don't destroy your benzene ring. We add here, what does that give? There. Now the chlorine's bonded to that carbon. But what's the stereochemistry of the carbon? We started with S, what's the product? What type of product do you get with SN1 here? Racemic. What does racemic mean? It's a 50-50 mix of R and S. Unless you want to consider the kind of that. Basically, it's 50-50 mix. Why? Because the chlorine attacks the planar carbocation. It's planar. Here it is. It either attacks from this side or that side. You don't attack backside. You don't attack front side. You're racemic. Because it's racemic, it would not be optically active. About the next one. should have asked you to predict the product here instead of just doing mechanism. This one down here, I want you to supply mechanism. Okay. In these handouts, there's often sort of points where I want you to do something, and usually that means I want you to do it for homework. Okay? Not to turn it in, but to have done it. And then the next day, we look at it and say, okay, was there any questions? Did everybody understand this? Let's talk about it. So look for that at each point. Also in these handouts, look ahead. And if there's questions that you're being asked to fill in the answer, please do that ahead of time so you get prepared for the next lecture. Really, I want you to do both of these. Okay. Here, it's a little bit unusual. We got potassium iodide and sulfuric acid. That's just two different reagents, but what do we need to do this chemistry? Up above, we needed the acid proton, and we needed the halide nucleophile. Those could come as HX, but they could also come as two different molecules. I mean, doesn't this supply H+? And won't that supply I-? That's what you need for this chemistry. So it doesn't have to come from HI. Don't tell anybody I told you that. BRC. Same thing below with that there. Lucas test. What type of alcohol do I have? Have you ever wondered that? You know? You're out having you're over 21, having a refreshment. Have you ever wondered what type of alcohol? Is it primary, secondary, or tertiary? Hopefully you're drinking primary alcohol. The other ones are quite toxic. Even ethanol is a little toxic, yeah? The Lucas test is a way to determine. The Lucas test depends on how long it takes for an alkyl chloride to form from the alcohol and separate from the aqueous medium. This test is sort of antiquated. It's not great, but it's good fundamental understanding of mechanism. The alcohol has to be water soluble. Okay? And the operating mechanism is typically SN1. That's important to know. It's done at room temperature. SN2s often need a little help, a little heat. Because it's SN1, which reaction is going to take place faster? If the OH is on primary, secondary, or tertiary? Yes, a tertiary alcohol will react very fast by an SN1 mechanism. You protonate, that ionization is going to be very fast. And then the halide will attack. Once you make the halide, for example here, this is water soluble. If we do the reaction with HCl, H2O soluble, what do you think about the water solubility of this compared to that? Less soluble in water, no hydrogen bonding. This actually is no longer soluble. This is going to separate, and you will now have two phases. Remember when we did the shaken, not stirred? As soon as you start shaking, you had two phases in the subfunnel.
Oh.
Okay? The Lucas test, based on how long does it take to get a second phase? If it's instant, pretty much you can have tertiary. Sorry. Does it not say this? Oh, it's on the next page. Sorry, I'm drawing stuff that's on the next page. There we go. By the way, the Lucas test also uses zinc chloride. Zinc chloride would be a Lewis acid. What's the definition of a Lewis acid? And a lot of times I'll ask questions, but I'll keep going. Because I expect you to say, okay, I'm going to go home and make sure I know what a Lewis acid is. Lewis acid. Here, tertiary alcohol, this forms instant. Separates into a new layer. Secondary, it's going to take 5 to 10 minutes, a little slower. A little like, why is it being sluggish? Primary, keep waiting. Okay? It probably ain't going to separate into another layer because the reaction ain't going to take place at room temperature. So it's a visual test, and we'll do a number of these kind of visual wet tests. Please look ahead. Remember from Organic 1, we'll next look at tosylates. To make an OH a good leaving group by converting it to a tosylate. We'll look at that. Again, this is a lot of review. And then we'll move to ethers. Let me know if you have any questions on the way out about the enrollment type stuff. I forgot to mention, we're checking in this afternoon. You got to have the check-in sheet from the workbook. Chemistry and Physics office. Check-in sheet. The instructions for check-in are in there. After check-in, we'll go downstairs and have NMR lecture. See you then, guys. Chemistry and Physics office. Yeah. $15.